There we go. Okay, so we're going to continue on in chapter 11, but the next major section here is going to be uniform rectilinear motion, okay? Now, we saw the last time we were together, when we have, for instance, an equation, and the equation we were starting with most often was describing the distance that would be covered as a function of time. And then we could do a derivative to get what the corresponding velocity was for that in relationship to time, and then also we could take it one more derivative and get the acceleration. Then we looked before we got done with the second example. We looked at having the acceleration as a given in our problem, and then actually doing an integral to get back to the velocity equation, and then also back to the distance. And then we had the opportunity to make the motion graphs or the motion curves that would represent all three of those equations for the motion. Now, because we know that we have certain conditions that are present, like in this case, uniform rectilinear motion, we have standard equations that have already been derived for us, so that we can just directly use them as we see fit, or where they're applicable for the problems that we're trying to solve. So that's what we're going to focus on here. And again, as I've stated before, and as we've looked at, this particular module, chapter 11, is really kind of a review for us. Most all of this should be things that you have already learned. So these equations coming up should look pretty familiar as well. So uniform rectilinear motion. Now, uniform rectilinear motion, we can have uniform motion in two ways. The first way that they're looking at here is where we have constant velocity. So constant velocity means that an object is moving along at a steady rate. It's not speeding up, it's not slowing down. And one of the things about constant velocity is that technically it's non-detectable. So for instance, if you're in a vehicle and you're speeding up, you're putting the gas pedal down, you're speeding up, you can feel that vehicle speed up, so you'll kind of tip backwards as the vehicle goes forward. All right. So you can physically feel that. Same thing when we put the brakes on and we decelerate. So that's a form of acceleration, but it just means that we're slowing down instead of speeding up. And there as well, when we put our foot on the brake, we can feel ourselves slowing down, where we're going to continue forward while the vehicle actually, slows down. But when we're at a constant velocity, we really can't detect that unless we see things going by. So if we have our eyes closed, for instance, in a car, and we're going, at a steady rate, barring maybe any bumps or curves that you're going around, but if you're going at a steady rate and you have your eyes closed, you're not even going to feel that anything is changing. Once you open your eyes and you actually, see the landscape going past you, as you look out the window, then you're actually moving. So velocity, constant velocity, means there's no acceleration. Okay, so that's kind of my whole point. You don't feel anything, because acceleration you always feel. So so that means that as time goes by, no matter if we're starting at the beginning, the middle, or the end of whatever time cycle we're looking at, that velocity will always be the same number. So if we're starting out at 2 meters per second, 1 second later, we're still at 2. 4 seconds later, we're still at 2, and so on. Okay. And it also means that our acceleration is equal to 0. All right. Additionally, when we solve for the distance that's actually covered as we're moving, we're going to notice that acceleration's not in there either, and we're going to be moving or covering distance at a steady rate as well. So as each second passes, we're going to be going at the same amount of distance covered, from 1 to 2 seconds, as 2 to 3 seconds, and so on. So what I wanted to do was add the equations here that we see to our equation sheet for uniform or constant velocity. So I'm going to go underneath our camera This is one of the problems we're going to look at. What I want to bring up is my equation sheet. Now, this is something you're going to want to add. The last time we were together, I said, you're making an equation sheet for me. You're going to be handing it in with your practice problems, and I'm not dictating what this looks like. I'm only sharing with you mine. But my expectation is that you're, pulling in the things. There might be extra notes on yours, or yours, like I said, might not look, it doesn't have to look exactly like mine. I'm not checking it for that, but I am checking that you have the main stuff down. So the section that I added here for constant velocity, motion for constant velocity, I just added here that my final velocity or my velocity at any point in time is going to be equal to whatever that original velocity was. So F just means final, and the O's mean initial or, original, if you would. I'm not sure that this book's use O's. Most textbooks that I've seen, excuse me, or used in the past have used I's for initial, but that's okay. So they use O's. Then you're going to notice that if we want to determine what is a distance that covered, so a final distance, over an amount of time, we're going to take whatever the initial, placement or position is that we have, plus whatever the constant velocity rate is that we're seeing on that body, times however much time that there is. Now, many times when we're starting, for instance, with an origin, and we're referencing that origin, a lot of times this is 0. So then it kind of cancels out, and we'll see that happen in many of the examples that we look at. So then our distance covered ends up being that constant velocity rate times however much time that we're actually, looking at. And then as you can see here, the acceleration when we're in a constant velocity state is going to be 0. Okay, so those would be the couple of equations that you would want to add to your sheet. So let me go back underneath our PowerPoint. And this is really just looking at once you're at a constant acceleration, you can, do those no, I'm sorry. This is uniform acceleration. I'm so sorry. I thought there was an extra thing here. So the other uniform motion state that we can have is where we have constant acceleration or uniform acceleration. So what that means is that we are accelerating at an even rate. So acceleration is velocity changing over time. So it just means that if we have an acceleration, for instance, of 1 meter per second or 1 meter per second squared, that means after every one of those seconds, we are increasing our velocity by an amount of 1 meters per second. So another constant acceleration state is going to be gravity, or if we have an item that is in a free fall. Okay, so if we're dropping something and it's in a free fall, that item is speeding up as it's dropping, and the rate of acceleration or how fast it's actually accelerating is going to be due to gravity. So whether we're in metric units, it's going to be 9.81 meters per second squared, or if we are in English units, it's going to be 32.2 feet per second squared. Okay. And again, you guys have studied that in your physics class and such. Now, when we have constant acceleration, okay, then we have a new set of equations where we need to, solve for our velocities as well as our distances. So these are the 3 versions of the equations that we would be looking at. So I'm going to go underneath, and I did add those to my equation sheet here. So when the acceleration is equal to being constant, okay, and it would be a known number. And again, if we are in a state where we are dealing with a free fall or gravity is affecting things, then that is a constant acceleration condition. So the first one here is our final velocity, or our velocity along, any amount of time. It's going to be equal to whatever the original velocity or the initial velocity is, plus the rate of acceleration times the amount of time that passes that we're interested in. Okay. And again, if we're starting from rest, this initial velocity would be a 0. Okay, and then we would just have the acceleration times the time. Then here's the calculating the distance. So if we want to know how much distance we cover when an acceleration is present, we're going to take wherever we start in relationship to the origin, plus the velocity that we're going at, or that we start at, times the time. Now, again, if these two are starting, first of all, position at an origin, this goes to 0 because the initial place is 0 where we're starting. And also, if we're starting from rest, so if we're at a stop sign, for instance, in our car, our initial velocity is 0. These two items would go to 0 and drop out, and then our distance would be calculated as 1/2 the rate of acceleration times the time squared. Okay, so again, this having these zeros is not uncommon. So if you're like, wait a second, I usually, solve for this and I'm only worried about this part, it's because a lot of times this will drop out because we're starting from rest or we're starting from an origin. Okay. And then the last one here, sometimes this comes in handy when we want to know what a velocity is over an interval of time at any one of those instances of time when we know what the position is. Okay, so there'll be an example or two where this one comes out in some of the samples that we go over tonight. Okay, so make sure that you get this one down as well. Okay. So I'll give you a second to add those to your equation sheets. All right, let me go back over to our PowerPoint. And these are the equations that we just looked at and adding those to our sheet. Okay. Motion on several particles. So we're going to find in the next example that we're going to be looking at is that we are going to be interested in not only the motion of an element or one particle, but we're going to be seeing the interaction between multiple particles. Now in this, or elements. So in this case, you're going to notice that they have some weights and pulleys. We're not going to be doing examples like that, but ours are going to involve, I think the first one we look at is going to be a ball in an elevator. Okay, so kind of looking at those in relationship to each other. And then also looking at car examples where cars are going at different rates and then they catch up to each other and we want to see, when that happens. So because of that, because we're going to be looking at things that are going at different rates, many times we want to know what is the relative motion. So one of the examples we will look at is when a ball falls in an elevator, what is going to be its relative velocity as it comes in contact with the floor of the elevator. So we have a couple equations here that we need to keep in mind with looking at distance as well as our velocity and acceleration when we're interested in elements that are relative or moving relative to one another. So I'm going to go underneath my camera and I added that to the very bottom here. So relative rectilinear motion, whenever we fully define motion, we are going to want to know where its position is. So that's going to be our x distances. Now, even though they're referenced kind of as a generic variable being x, we can reference them vertically as well and call them y's. And we will see that in an example or two that we have. So this is just basically distance, but it's a horizontal distance. So it's going to be the position of B is going to be equal to the position of A plus vectorially the position of B relative to A. So over here on the side, we can see that here's the position of B, okay? Here's the position of A, both of which reference the origin. And then the position that's between them, or one relative to the other, so B being relative to A or dependent on A, measuring from A, is going to be that distance between, okay? And then we can take that very same concept or that order, and we can do the very same thing for velocities and accelerations. And we actually saw the application of this back when we were in last term in kinematics. So if you had kinematics with me, you have seen this before in terms of velocities and acceleration. So really that very same thing. Okay, so we'll see that come up in an example very soon. Okay. So let me go back over here. And I think, yep, that sets us up for our first sample problem. And our first sample problem is going to be problem 11.5 in our book. This is going to be found on page 640. Here, I actually have it underneath my camera right now. 641. And I also have it here. It's a couple of slides. I'm going to reference the actual page out of the book. So I'm going to go underneath my camera right now. This over to the side. I'll pull this in. And one. There we go. Okay. So what we have here is we have a ball that's in an elevator shaft, okay? And it says that the ball is going to be thrown vertically upward with an initial velocity of 18 meters per second at a height of 12 meters above ground. So what they've done over on the right-hand side is the first illustration that we see here. This is a figure that is referencing just the position of the ball in relationship to the ground, which is considered our origin or our zero, okay, as far as position, okay? Then we're going to notice that the next picture directly below it, oops, this is caught, directly below it, this is an illustration of our elevator shaft, okay? So our elevator floor is right here, okay? And in relationship to the ground or zero, this is going to start out 5 meters up. And the motion of this is going to be at a steady rate, and that's what this is, velocity of E or velocity of the elevator. And it's going to be at 2 meters per second. So this is going to be going up at an even rate, okay? So this is the ball by itself that's being thrown up at that 18 meters per second. And then at the same time, our elevator is moving at that steady rate of 2 meters per second. Okay. Now up here, what it's saying is they want us to determine when and where. So when, that's going to be the time. What is the time that the ball is going to hit the elevator? Okay. So the elevator floor. So when is this ball? Okay. And actually, this is the illustration. When is that ball going to come in contact with that elevator floor? Okay. So what is the time that happens? So that's going to be a T. And then where is going to be, okay, how far above the ground does that happen? Okay. So when and where, and that's going to be a Y distance for us. Okay. And then the other part of this problem is they also want us to figure out what is the relative velocity of that ball with respect to the elevator when they hit each other. Okay. So, yeah, so that's what we've got. So what we're going to start out doing is we are going to identify what we're given and what we need to find, and then we're going to go through the process. So this is sample problem 11.5. Okay. And again, we're going to be doing 4 problems tonight. So this is our first one. Now, as far as givens, okay, so these are our givens. And we're going to start with the ball because we have 2 elements here. Okay, we've got the ball and we have the elevator. So let's start with the ball. Okay. We know that the original velocity of that ball, the initial velocity, it is being thrown up at 18 meters per second. And I'm just going to show that going up. Okay. And we're going to start right now. We're going to set our convention. And this is, as we know, pretty standard, but it's worth identifying in our problem is that up in this problem is going to be positive. There aren't any, you could add an X here if you wanted to be positive, but there are no X directed anything. So positive is going to be going up. So anything that's being directed down is going to be negative. Then we are also told that our Y distance, the position of that ball when it's being thrown up, is going to have an original position of 12 meters above the origin. So that's considered a positive value too. I'm not going to put a positive out front, but because it's, it's an assumed positive, that means that it's above the ground level. So in this illustration, 0 is here or origin is there and we're 12 meters above. Okay, that's where we're going to actually, push the ball up or throw the ball up at that point. We know that because, pull this back, That ball, when it's in the air, under its own accord, even though we are, throwing it up, gravity is working on it. So that means that there is an acceleration, a constant acceleration on that ball due to gravity. Now, when we look at our units here, our units are being given in meters and seconds. So we are in the metric system. In dynamics, we're going to be working in both. So when you're doing problems, just kind of make sure because our acceleration is the number is going to change. So when we are in the metric system, our rate of gravity for acceleration is going to be 9.81 meters per second squared. Okay, so if I go over here, my acceleration on the ball, okay, that's why I'm putting the B there, it's going to be equal to a negative 9.81 meters per second squared. Okay, the negative is important because this is directed down and up is positive, gravity is down, so it's going to be negative. Okay, and then we're going to have to determine, as we know, we got to find where that ball is going to hit the elevator. So we want to know at any given point what is the position of that ball. So we're going to say YB is equal to question mark. We're going to have to find that. Okay. And then we'll talk about how we get that and such. Okay. So as far as the ball, those are the things that we know. Now we're going to look at the elevator. Okay. All right. So the elevator, it said that the velocity that the elevator is going is equal to 2 meters per second, and it's going up and it's constant, okay? It's constant. So what that means to us is the acceleration of that elevator is 0, okay? So every second that goes by, that elevator is still going 2 meters per second, 2 meters per second, 2 meters per second. It is not speeding up. It is not slowing down. Okay. All right. And then its position, we need to find out when it's going to hit the ball. So we're going to call that YE. Okay. We need to find that. And then something that we are given, oopsie, is the original or the initial position of our elevator is 5 meters above the origin. So if we go over here, the elevator is the second figure, okay? Here's our origin, and we are 5 meters. We're looking at this when it's starting out at 5 meters above the origin, and that velocity is, going at an even 2 meters per second every second. Okay. Now, what we want to find. There's two parts to this question or to this problem. So part A is we want to know when. So I'm going to put in parentheses T because we want to know what is the time. Okay, when and where, which is going to be our Y dimension. Okay, vertically, when and where the ball and elevator hit one another. Okay, so I'm just going to put hit. So I end it there. Okay. So when do they hit or collide? And that is what we see in the bottom illustration here. We want to know how much time as the elevator is going up and the ball is going up, how much time does it take for those two to hit? And what is that distance above the origin going to be? So that's part A. Part B is going to be what is the relative velocity? And that's going to be V ball relative to the elevator, okay? When they hit, okay? So those are the two things that we're going to find, like the two big, well, technically three things, the time, the place, and the how fast, okay? So I'm going to kind of separate this because those are our givens and knowns from the problem statement. Okay. Now, the next thing we want to look at is what are the units and if we have to do any converting, because as I've kind of alluded to and stated, and we saw the last time we were together, I'm giving you a break on units, but that means that we have to have consistent units set up right away in the problem. So in the problem that we have here, you're going to notice that we're working in the metric system. So all of our distances are in meters and all of our times are in seconds. Okay. So you want to check that over to make sure. You want to make sure that there's no kilometers per hour or something like that. Because if there is anything that's other than meters and or seconds, then that means that we have to do some converting up front. And then as we go along, we don't have to worry about doing any conversions midway. So right now we are all set. Every one of our units are in meters and in seconds. Okay, so no conversions to do for this particular problem, which is good. Okay, now as we look, since we want to find, if you would, let's look at this last one down here. Since we want to find when and where that ball is going to hit the elevator, if you notice that on the left-hand side, they have YB. That is going to be the distance above the origin that the ball is. Okay, so it's position above the origin. And then we have YE, same thing. It's position above the elevator. So what we're going to do now is we're going to look individually at the motion of the ball by itself, and we're going to see if we can calculate or determine what is the equations or what things do we know, and we can fill in based on those uniform motion equations that we looked at for the velocity and also for the position. Okay, and then we're going to do the very same thing for the elevator. Okay, and then once we have those, we're going to find the position and the time by setting those two equal to each other. Okay, so let's start out by looking at the ball. Okay, so we're going to look at the ball motion. Okay, and we know the condition here of our ball because we are throwing it straight up, right? And what is acting on it is going to be gravity, okay? And gravity is that constant acceleration, okay? So our condition here, the ball's motion is constant acceleration. And that is due to gravity, okay? That's due to gravity. And as we stated up here in the givens for our ball, we identified the rate of gravity as a negative 9.81 meters per second squared. So when we see it pull in, when we see A as our variable in an equation, we're going to insert that number. Okay. All right. So first one we're going to look at, and really where we're going over on our equation sheet, we are in this area right here. Okay. So we are going to start with the velocity of the ball anywhere along, its track, if you would. So we're going to say velocity of B is going to be equal to the original velocity or initial velocity of that ball. And in this case, it's going to be when we throw it up. Okay, so when we actually throw it up, that's going to be the velocity we put here, plus any acceleration that's on it. In this case, it's the acceleration of gravity. So it's the acceleration on the ball. We know that to be up here. Times however, many seconds we're looking at identifying or analyzing this at. Now, in this case, you're going to notice I wrote out the equation. So just like other classes that you've had with me, we're not going to do units inside the problem, but you always have to identify whatever equation you're working with in its variable form first. So that's what we have written out right here. Okay. So now what we're going to do is we're going to input any values that we know. So we know that our original velocity when we throw it up is 18 meters per second, but you don't have to put the meters per second. And then we're going to say plus the rate of gravity, which is negative 9.81. Okay. And then we don't know the time at this time. And that's why we're using this. We want to end up solving for time in a little bit. Okay. So T is going to go there. Okay. So now what we're going to do is we're going to then say, okay, the velocity of B or the ball at any time, along its path is going to be 18 minus 9.81 times T. Okay. And now that's as far as we can go because we don't know velocity and we don't know time. There's two variables there. So we're just going to let this kind of hang out and we'll come back and reference that. Okay. Now, we already know that the acceleration is gravity. We now have found out here's the equation for the velocity. So the last part of fully defining that motion is looking at where is it located or what is its position. Okay. So if we look here, there are two equations that we can use, or I'm sorry, there's just one equation. There's two for velocity, one for the position that is, due to the rate of acceleration. So what we're going to do now is we're going to use this equation to determine position. So here we have y of the ball. Now, this is determining its position in a vertical fashion. So even though our generic is x, as I stated earlier, we can be vertical as well. And so in that case, we call the variable y. So yb is going to be equal to y initial or original at b plus the velocity original at b times the time plus 1/2 times the acceleration times the time squared. Okay. And now we're going to input, any values that we can put in here. So what we're going to do is the position original. Now, our ball, the origin is going to be the ground, and it starts at 12 meters above the ground. So our y original or initial is going to be that 12 meters. So we're going to put 12 right here. It's above the ground. It's in a positive orientation, so we keep it as a positive number. The next one that we have here is going to be plus the velocity of the initial velocity of the ball when we throw it up. If we look here, that is going to be 18 meters per second, but we're just going to use the 18. Okay. And then we're going to multiply it by the time. We don't know what the time is right now, right? So we can analyze this at any increment in time. So that's going to be the variable for the time. And then we're going to say plus 1/2 times our acceleration. Our acceleration is a negative 9.81. Okay. And then we're going to take the time squared. Again, we're going to input an increment of time. All right. So now we can, do the distribution. So the 12 stays plus 18t, but then we're going to multiply 1/2 times a negative 9.81. So that's going to be a negative 4.905 t squared. Okay. And then this is as far as we can go because again, we have two variables, that distance in the y direction for the ball at any, increment of time. Okay. So questions so far. So that's just looking strictly at the ball. Now we're going to look at the elevator. Okay. So the elevator, I think I should be able to fit this down here. The elevator motion, this one, as we stated earlier, does not have acceleration. This is a constant velocity, okay, condition. So I'm just going to identify that here. Constant velocity. So in this case, there's no acceleration, okay? And if we go back over to our equation sheet, we're over here now, okay? So since we know the acceleration is 0 right away, so that's defined for us. That's one part of the motion. Now we just want to identify the the velocity and its position, okay, in terms of time. So our velocity of our elevator at any point is going to be equal to the 2 meters per second. Okay, I am going to put the meters per second here because it just looks weird that it's not there, but in the equations when we're using it, we will, we don't have to worry about the units. But this is going to be at any increment in time, it's going to be 2 at 1 second, 2 at 2 seconds, and so on. Okay. Now, elevation or the y distance of E, okay, at any increment of time is going to be equal to the initial position of E above the origin plus the velocity of E times the time, okay, times the time. So our 2 is going to go in there because it stays the same. And then we look, was this above the origin? So if we look up here, we do have 5 meters, and you're going to notice that in that second figure, it is 5 meters above the origin here, okay? So we are just going to input those values there. So this is going to be YE is going to be equal to 5 plus 2T, okay? And then that's as far as we can go there. All right, now I'll kind of put this isn't really an equation, it's always 2. Okay. So looking at each one of our elements that are interacting with each other in this problem separately. Okay. So now what we're going to do is we are going to find the time at which that ball and that elevator hit. Okay. So we're going to turn this over, and at the moment that they're going to hit, I'm going to zoom in here, this illustration, we know that the distance from the origin will be exactly the same for each one. So our YB is going to be equal to our YE. Okay. So, see, it's a little far. There we go. So we're going to say YE is equal to YB, right? So now what we're going to do is we're going to put from the previous page, our YE was equal to 5 plus 2T. That's going to go on the left-hand side of the equal sign. 5 plus 2T, okay, is equal to YB, which is the position of B, is this equation right here, okay? So it's going to be equal to 12 plus 18T minus 4.905 T squared. Okay. And now what we want to do is we want to combine elements. So what I'm going to move my 5 and my 2T to the other side. So that means 0 is going to be over here. This is going to be equal to 12 and 5 are going to be able to combine. So I'm going to say 12 minus 5 because it's positive over here. It's going to the other side. The 2T and the 18 can combine. So I'm going to say 18T minus 2T because it goes negative on that side. And then minus 4.905 T squared. Okay. So then I'm going to combine these elements. So 0 is going to be equal to 7 plus 16T minus 4.905 T squared. And our only unknown here then is our T value, right? Now, you're going to notice that this is in that quadratic form, right? It might not be in the order, but we have the square, we have the regular, and we have a constant. So in order to find the time when these two are equal to each other at 0, we can now use our Excel spreadsheet to find it, okay? So I am going to, oh, I don't have it open. I thought I did. I'm going to open up Excel. And what I'm going to do is I'm going to grab one of the spreadsheets, any one of them that I had for, the position, the velocity, acceleration. And that first time tab was where we had that quadratic form, okay? So all we're going to do here is we are going to utilize this just for this little calculator, okay? And I already used it earlier today, but what I'm going to do is I will just take these out of here. Okay. And we're going to put in our A, B, and our C. So if you recall from our quadratic form, go back underneath. Okay. When we have our quadratic form, where the square is, that's going to be the A value. Where the X is in this case, not the square, is going to be our B, and then where the non-variable is going to be our constant. Okay. So going back over here, our A is going to be equal to the negative 4.905. Okay. That's what the square. Our B is the 16, and our constant is the 7. Okay. So you're going to notice here we get two values for T, okay, being equal to 0. The first one is that negative value. So again, when we're looking at time, in this case, it can't be a negative. We're not on the other side of the 0, if you would. So the only one that's valid here where the time is 0 is going to be 3.65 or 3.65 seconds. Okay. So I'm going to go back underneath here, and I'm just going to put a little star inside, and I'm going to say from Excel. Okay. T is equal to 3.65. And I guess I held two more. So 3.6527. Okay. And that's going to be seconds. And I'm going to put a box around this because this is an answer for part A as to when the ball and elevator collide. Okay. So we've got the time. We just that's one of the variables that they were asking for. They're like, when is that ball and that elevator going to collide? So at 3.6527 seconds after we get started, they're going to hit one another. Okay. Then the next part of this is where. Okay. Where are they going to collide? So we are going to use either one of these equations, whether it's the E equation or the B equation. So whether it's for the ball or for the elevator. Now, if we look, those position equations, this one's longer than that one. So I'm just going to use the easier one. I'm going to use the YE is equal to 5 plus 2t to solve for where that happens. Whichever one you choose, they're going to equal each other. So you can test that out if you want. Okay. So we're going to say YE is equal to 5 plus 2t. And we're going to use that value now for, for the value of t. Okay. So this is going to be equal to 5 plus 2 times 3.6527. So my YE should come out to 12.305 meters. Make sure when you show your final answer, just like we have for the time, inside, don't worry about the units because again, we verified that they're all in the correct form. But when we report a final answer, like when it's answering one of those questions, then make sure you put the appropriate units. So T is equal to the time as to when the ball in that elevator, we add the second. So here as well, the position above that origin is 12.305 meters. So make sure you add the meters. So I'm going to put a box around this. This is the second part of part A. And this is the where the ball and elevator collide. Okay. So we have part A done. Any questions here so far? Okay. If not, right? Then we're going to go to the second part. So the second part of this problem wants to know what is the relative velocity of the ball with respect to the elevator when the ball hits the elevator. Okay. So the ball went up, it thrown up, and it's going to start coming down, right? The elevator is moving up at a steady rate. And now we want to know, okay, right at that moment when that ball hits the elevator, what is its relative velocity? Okay. And the relative velocity means that the elevator is going up, the ball is coming down. Now, what is the effect of those two hitting each other? How fast is that ball going? Okay. So what we're going to do is we're going to use that relative velocity equation, and it will sound familiar. So from our sheet here, okay, you're going to notice that we have velocity of B, which is out here, is going to be equal to A plus vectorially B relative to A. All right. Now, if we take and we isolate the B relative to A, we're going to put this on the other side. Okay. So we're going to start with the, I'm going to write first relative velocity. Okay. So we're going to have the velocity of the ball relative to the elevator. So the B comes first and the elevator second is going to be equal to, okay, then it's going to be the velocity of the ball minus the velocity of the elevator. So if the ball came first, if it's the ball relative to the elevator, then the ball comes first and we subtract the elevator. If it was the elevator relative to the ball, it would be EB and then EB. All right. So the order does matter on how they ask for it. So ours is ball relative to elevator. So it's B minus E. Okay. Now we already know that the velocity of the elevator is 2 meters per second. That's constant. All right. So that doesn't change. So we're going to know that's going to be 2. Okay. And the velocity of the ball. Okay. The velocity of the ball. If we look back, we can calculate the velocity of the ball at any point by using the equation here. Okay. 18 minus 9.81 t. So what I'm going to do is right below here, I'm going to do the equivalent 18 minus 9.81 t, okay, minus 2. Okay, that's it. And then now we're going to combine what we can, all right? And then we're going to input the time that we got from above. So we know that it collides at the 3.6527 seconds. So we're going to input that here. So this is going to be 18 minus 9.81 times 3.6527 seconds minus 2. No variables here anymore. So now we can solve for this value. So go ahead and calculate for the velocity of B relative to E. And I'll write mine out. I'll do mine. And then we can compare. Okay. I got a negative 19.58 meters per second. Now remember, this is velocity, so its units are meters per second, and we're reporting a final answer. So that means that we have to add the units here. You don't need to put them in here, but make sure that they magically appear at the end. Okay, so any final answers you're reporting out have to have a variable identified, so in this case, the velocity of B relative to E is equal to the value plus the units. Okay. Did everybody get the negative 19.58?
I did.
You did? Okay, excellent. Now, what does that mean to us? So when we have floor of the elevator and the ball hitting each other, okay, the relative velocity being negative, remember at the beginning of our problem, we said up was positive. So that means that this velocity is going down. So the velocity of B relative to E is equal to, and I'm just showing it going down, the negative 19.58 meters per second. Okay. Okay. Any questions about that? You got it too, Tyler? Thank you. Oh, you've got 8-3. Oh, you do. I don't know. Josh, you got what
I
I
went
got?
back. I went back and did it again. I missed something. It is 8-3.
It is 8-3. Okay. I'm gonna trust you guys. I'm gonna trust you. Yeah, I'm not gonna redo it. So if we've got three people that already that got that same answer. Oh, four. Nia got that as well. Okay, thank you. Okay. All right. So any questions on 11.5? All right. If not, then the next example we're going to be going over is 11.6. So I'm going to stop the recording here so that this is available if you need to go back to it, and then we'll start a fresh one on the next example.